Okay. All right. Polynomial functions are functions of degree 2 or higher, so quadratics, cubics, 4th degree, 5th degree, and so on, having smooth and continuous graphs. So here are two examples of graphs that are not both smooth and continuous. This one I would say is smooth, but we lack continuity because it has a break in it, right? This one is continuous, but it lacks smoothness because it comes to sharp points. Okay? So these are just two examples of not. But you know your traditional polynomial functions and what they look like and all that good jazz. So vocab words to know. Continuous. A continuous function, and we'll do obviously much more with this. That's a huge calc word. Are functions where you can trace infinitely without ever taking your pencil off the paper, essentially. That's the loose elementary definition. We're going to talk a lot about end behavior, which I know you guys know what that means. The roots or the zeros or the x-intercepts, that's vocab you're familiar with. And multiplicity. Do you know what multiplicity means? Does anybody know what that refers to? How many times it occurs? What's it? Yeah, the root, exactly. So it's only one root, but it might have a multiplicity of 2 or a multiplicity of 3 and so forth. So we'll talk about multiplicity and what happens if something is a root or a solution kind of multiple times. All right, so I know that I'm pretty sure I teach my Algebra 2 kids end behavior a little bit differently. I think you guys did like number line tests. Does that sound familiar? Where you like did little number lines and you would put your roots on there and then you do like plus, minus, plus, like that. Did you do that? Okay, I don't do it that way. You can continue to do it that way. But for my non-advanced Algebra 2 kids, I don't do it that way because, I don't know, I just don't. So if you were sketching a graph, you would first need to, find your zeros. So we're going to factor this by grouping. And we have 3 zeros. Each with a multiplicity of just 1. Okay? So, as far as a multiplicity is concerned, if something has a multiplicity of 1, it's just going to cut through kind of evenly or smoothly. I'll just put M1. If something has a multiplicity of 2, it's going to bounce. So I'm going to put M2 for multiplicity of 2. Do you know what something does if it has a multiplicity of 3? Any guesses? Andrew? Not just like that. It will go through, but there's a little bit of a unique way. This one kind of smoothly goes through. If it's a multiplicity of 3, it's going to approach the x-axis as if it's going to be the top peak of like a quadratic section. But then it kind of inverts and goes through and looks on the other side like it's the bottom of a, quadratic parabola. Does that make sense? So, loosely speaking, I don't know what I call this. It just goes straight through. Loosely speaking, this is a bounce. That's not a math vocab word. That's just like a very elementary word just to help us trigger that. And this one, what would you call that? I mean, you can call it whatever you want to call it because you're the ones that have to remember it. What would you call that, like inverted motion? Tell me, Mackenzie, what's your gut tell you? Is it a funny word? Just going through?
Yeah.
But then how would that differentiate from this? Squiggle! That's what I've always called it a wiggle, but squiggle really makes more sense, don't you think? The only reason I called it a wiggle is because the guy I used to teach with called it a wiggle, and I just went with it. I just wrote squibble. I didn't mean that. Squiggle. Spell squiggle. Do you think that's right? I have no idea. You think that's right? Squiggle? Is it a real word? I'll let you know by the end of the period if that's a real word. But we all know what it means, so it might as well be. All right. So, as far as this one is concerned, if I'm sketching a graph of this, I have a root at -3. That's a single root. A root at -1. That's a single root. And a root at +1. That's a single root. This is where you guys would do your number line test to decide, is it positive or negative here? Is it above the x-axis or below? Is it positive or negative in this stretch, above or below? I don't do it that way. I kind of use this. You can memorize what I'm about to go through, or I would argue that you already know this, because your odd degree go-to function is a line, right? If you have a line with a positive leading coefficient, what does that mean as far as its overall slope is concerned? Its slope is what? Aiden? Right. Always positive, but you're not going to have that with polynomial functions because it's going to go up and down and up and down and up and down. But overall, start to finish, if you're odd, your overall slope is going to be positive if you have a positive coefficient, right? So that starts low, meaning from -infinity, and ends high, meaning to positive infinity. And you know, if you have a y equals -x with a negative leading coefficient, the overall slope is negative. Starts high, ends low. As much as I can, I like to capitalize on what people already know and make that connection. It's just less to remember in the end than giving you a totally different strategy. Okay? In your go-to even degree function that you already know about, even prior, obviously, to algebra 2, is y equals x squared, which is a parabola. And we just talked and reminded you yesterday, if it's a positive x squared, this whole thing opens up or down. Positive A means it opens up, exactly. Which, for even degree functions, although they won't be as basic typically as a quadratic, they'll have a lot of fluctuations in the process, but the picture in its entirety will open up, which means it starts high, ends high. And likewise, a negative x squared has gotten flipped upside down. So overall, you would say it opens down, starts down, ends down. In general, odd degree functions have opposite end behavior. I'm sure that's something Mrs. Zigai pointed out to you. They go in opposite directions, whereas even degree functions go in the same direction. Okie doke. So if I'm looking at this one, what's its behavior, Nate? How does it start? How does it end? Right. So I'm going to start coming from negative infinity, and everything is a single root, so I'm not bouncing, I'm not squiggling, I'm just going straight through, and at some point I have to turn around, and then at some point I have to turn around, and there we go. It should naturally end up that whichever way you started, you should end the appropriate way, as long as you don't inadvertently insert a bounce or squiggle or something. Okie doke. Any questions? Okie doke. Show that this polynomial has a 0 between 2 and 3. How would you go about doing this? We have no calculator. We want to show somehow that between 2 and 3, this graph crosses, whether it goes this way or this way, I'm not sure. How would you go about showing that, given that you don't have a calculator and given that this is not really solvable? Aiden?
You would put in 2 and 3, and then one came out for x and one came out for positive and one came out to be negative, and you would know at some point it crossed.
Okay, let's see. So he's saying plug in 2. You get 8 minus 4, which is 4. 4 minus 5 is negative 1. And if you plug in f of 3, you're going to get 27 minus 6, which is 21. 21 minus 5 is 16. So that gives us a point 2, negative 1, and 3, 16. So like he said, one of those is negative and one of those is positive. And polynomial functions are always continuous. It's not like there's going to be a break and we're going to jump over the x-axis. We have to really just connect the two dots. So of course it's going to cross a 0, and therefore we've proven it. So since f of 2 is negative and f of 3 is positive, and f of x is continuous, that's key. Because if this was like a piecewise function and there was some break in action between 2 and 3, you'd have to reconsider. But since it's continuous, we know f of x equals 0 somewhere between x equals 2 and x equals 3. Good? And lastly, yeah.
This wouldn't work if the 0 was bound split.
No, it would not. But this is the way this is phrased, it's sort of a leading, it's kind of already telling you it does. Show that it does. Do you know what I mean? Prove that it does, which means they're pretty much, saying it does have a 0. Prove it. You would not be able to prove it in this fashion if, you're right, if it was a double root somewhere. And triple, you'd be fine. Double, you'd be not. I'm trying to think. I don't think I've ever seen one like that. Hopefully, if it's a double root, there's a bigger chance that it's factorable. But if it's an x to the 5th polynomial, then you're kind of that many degrees away, so maybe it even still wouldn't be. So, good point. That's a good point. But I don't think it's going to come up, just so everyone's aware. All right, and on the last one, take a minute on your own, sketch a graph of this, and we'll see how you do. Raise your hand if I did not get homework from you. You can do that. All right, Bridget, where's your roots? And what are their multiplicities? Multiplicity of 2. And what's your end behavior like? Right. Positive even is like a positive quadratic. So it's going to bounce off the multiplicity of 2 and bounce off the multiplicity of 2. And there we are. Starts high inside. And your y-intercept is? With polynomial functions, this is real easy. 1. Because it's just your constant at the end. If it's in like a simplified polynomial form. So you should label that. Any questions on that? What did this factored into this, right? So x plus 1, x minus 1, x plus 1, x minus 1. And you see x plus 1 squared, x minus 1 squared. So that's multiplicity of 2 right there. Okie doke. Any questions? Oh my gosh, we have 13 minutes.